Hey all, I want to say thank you, and I'm looking at my lead slide and noticing that I have coastal wetlands, and I need to identify a very specific difference in definitions. I follow a lot of wetland scientists, and when they're talking about coastal wetlands, they are talking about tidal wetlands, whereas Fish and Wildlife and some of the larger groups, when they're talking about coastal wetlands, they're talking about all wetlands within a coastal watershed, which is what Jovian was talking about. So there's a significant difference. Anyway. Once again, NACIS has put together an amazing conference. Thank you all to all the folks who have worked hard to organize this event. I know it takes many hours in advance preparation, and it's great to be here. As Molly noted in my intro, mapping water is an abiding passion, and I am super excited to be part of this panel. It's been great information. Before I begin, I'd like to acknowledge that the land we are meeting on is the land of the Eastern Band of the Cherokee, the Osage Nation, and the Shawnee. And I'd also like to thank NACIS for the donations to the Indian Land Tenure Foundation, nativeland.ca, and the Kentucky Native American Heritage Commission. In support, I will give my own donations to these same groups. About 850 miles to the east-northeast of here is the Great Marsh. It is a salt marsh estuarine complex protected by sand barrier spits that enclose Plum Island Sound and Essex Bay. It is the largest salt marsh in New England and is struggling with sea level rise as well as the impacts and limitations caused by human development. I created this elevation-based representation of the salt marsh complex in 2022. Many of you have already seen this. But it remains a template from which I have based other wetland work on today. This afternoon, after I give a brief overview of wetland geography and its values, I will summarize the workflows I use to bring the Great Marsh into the forefront of the visual hierarchy and discuss the pros and cons of this approach. As many of you already know, but I'm going to review some of this anyway, wetlands are lands transitional between terrestrial and aquatic systems. They are almost always on a moisture gradient and can be dry for parts of the year. They form in depressions along the edges of rivers and streams where salty tides flood the shore and over ice sheets. They vary from large, bald cypress trees to circumpolar boreal wetland complexes to coastal wetlands. They provide invaluable ecological services such as filtering and cleaning water, protecting adjacent environments from extreme phenomena, and providing habitat for a diverse array of species. While there is a continuity of landforms traced by water, wetlands often have unique textures and colors compared to their neighboring habitats. And despite their propensity for being flat, high-resolution elevation data picks up their subtle textures on large-scale maps. I think you can probably see the labels on the slide. Coastal blue carbon. When considering climate change and carbon budgets, the salt marshes, mangroves, and seagrasses are known as coastal blue carbon. This is unique from the green carbon of terrestrial forests and the black carbon that contributes to global warming, the soot, the pollution. Blue carbon can be 10 times more effective at absorbing and trapping carbon than tropical forests. And even though coastal blue carbon environments cover just 2% of the total ocean surface, they account for 50% of the ocean's carbon absorption. In short, both coastal blue carbon and deep sea carbon are carbon sequestering and storage rock stars. This is really important. It's not something that I take lightly. Anyway, the wetlands, despite their variety or how good they are at sequestering and store carbon, are often depicted on everyday maps with this symbol. We're all familiar with it, and it's beautifully illustrated in this 1946 book, Elements of Topographic Drawing. I particularly like the guidance for how to draw the herbaceous growth vegetation seen at the top. You have to imagine it being cut off by water. The value of this symbol is its near universal recognition. It uses horizontal lines to connote a calm water surface and easily recognizable monocot vegetation, which we often see in wetlands. When we see this on a map, we can anticipate soggy feet if we were to walk through it. But seeing wetlands mapped with this symbol yields a very different experience than seeing wetlands in person. As an abiding advocate of shallow water environments, I'd like to crack the window open, even just slightly, on new ways to represent wetlands on everyday maps that yield a little bit more information to the viewer, which then can benefit the wetlands. Elevation data is frequently used for representing and modeling all types of hydrology. For example, Dan Coe, our next presenter, has done magical work using elevation data to show the imprint that water has left on the landscapes. There is no reason why this data can't be used for representing wetlands, and there is every opportunity to bring some of this styling to wetland cartography. When considering data sources to do this with, I find it useful to understand the elevation gradient, how it's associated with the tides. Coastal wetlands typically occupy the intertidal zone, seen with the purple text in the profile. And salt marshes have two important elevation-dependent regions, the high marsh and the low marsh. The high marsh generally has higher species diversity than the low marsh and is the area garnering, whoops. Sorry about that. I didn't know that did that. Garnering more attention. Because of their elevations, the entire intertidal zone can be described and depicted with elevation data, and there are usually two sources for gathering data for coastal wetlands, USGS and NOAA, or I'm not going to go through these. The 1 meter elevation data offered by the USGS has broader coverage, is more consistent, and yields greater detail on larger scale maps. For gathering approximate extents from the wetlands, the vector-based National Wetland Inventory, the NWI, is the de facto source. So if you're starting out with a map and want to know if you've got wetlands there, bring in the NWI layer and filter it for wetland types. And you'll see if you have wetlands, and then see if there's elevation data there. What this profile doesn't portray well is how flat this environment can be. In the Great Marsh, the height difference between high and low tides is about 3 meters, but the marsh extends about 8 kilometers inland. That's pretty flat. Let's see. In contrast to identifying wetlands, wait a minute. Okay. In contrast to identifying wetlands on a gradient, for example, riparian systems which flow, wait a minute. That's like a different slide. Okay, I think it is right. Okay, in contrast to identifying wetlands on a gradient, for example, riparian systems which flow adjacent to streams and rivers, using elevation data to map tidally dependent coastal wetlands has the advantage of starting vertical counts from a nearby zero. What I mean is that riparian systems are bordering rivers and streams, and they are not from zero going up. They are adjacent to streams and falling in elevation as you go down in two planes. From my experience, real-time tidal heights don't always transfer well to elevation data, even when adjusted to local tidal datums. For large-scale maps, by current practice is to establish relative elevations by comparing contour lines and hillshade from satellite imagery. For the Great Marsh, USGS 1 meter data, zero aligns with the low edge of the marsh, which in this case is not mid-tide and it's not low tide. It's somewhere in between. You can see that on the elevation, on the satellite imagery. Based on this, I use that data to detail the salt marsh, the vegetated portion, because it covers it, and use NOAA's 3 meter data to represent the water at approximately low to mid-tide, which obscures the tidal flats. Depending on what you're doing, hydroflattening, which I'm not sure if you can pick up on this screen, most of you should be familiar with it, but hydroflattening can be an aid or a problem when mapping water. Sometimes it's helpful, sometimes it's not. Hydroflattening is required by the FGDC for all USGS elevation data, but not NOAA's data. This means that all water bodies greater than 0.8 hectares or 2 acres are flattened with relevant elevation values to create a smooth appearance. Here, the hydroflattened surface begins just below the vegetated low marsh and at the point where the tidal flats are present. So, and if you're trying to do adjustments on this, the hydroflattened surfaces do not run well through the tidal calculations, the tidal change calculations. The Great Marsh Complex, seen in this aerial, the dunes seen on the right, the estuary seen at low tide, and the salt marsh are unique habitats that vary in texture and color and topography, but don't vary much in altitude, except for some of the dunes. Some of the dunes are a little higher. The lack of elevation change makes it challenging to control the profiles and detailing, so I created separate elevation layers for each of these environments. The layers are shown here, and for visibility via projector, I'm using just a portion of the map to demonstrate the technique. I will work up from the bottom, but only focus on the salt marsh, dunes, and hydrology layers. To eliminate the data above the salt marsh, I use raster calculator in QGIS to apply the equation seen in the slide. It's a pretty simple equation. Here, everything above 2 meters is now no data. Because this starts at about, well, it starts at 0, but the marsh goes up to 3 meters, so it's missing a meter of low tide. Here, everything about, my hypsometric tints reflect the moisture regime of wet to dry. For the wettest vegetation portion, the low marsh, I used a brighter blue-green that suggests a vegetation that's a vegetated but watery environment, then transitioned to a slightly greener yellow to blend with the drier upland colors. Keeping it bright helps to pull this information to the top of the visual hierarchy. Since it's a standalone layer, I don't need to use the multiply blend mode, which preserves the colors I choose, which is a huge asset. Creating the hypsometric tints for the dunes was fun. Even though it's looking east, I imagine being on west-facing dunes overlooking the ocean in awash in sunset colors. I then used fairly strong hill shades to reveal the warm rosy and yellow dune structures. And even though I'm not showing much of the dune, it's an incredibly important part of the system. Without the dunes in place that are deposited by the ocean, the estuary and then salt marsh behind it would not form. So that it is the reason why the estuary and marsh exist behind it. The 3 meter QDEM data set available for this location incorporates fairly recent high-resolution topography survey work. Not all QDEM data has this same level of detail, which was lucky for me. The higher resolution data helps portray the flowing depositional patterns created by the high-energy 3-meter tides. Choosing a color ramp near the redder end of the blue spectrum complements the greens of the salt marsh and clearly identifies this as water as opposed to vegetation. And dropping the saturation lowers it a little bit in the visual hierarchy. I really wanted the salt marsh to stand out. For those interested in the new blue topo data, I'm not sure if everybody's read about it, but most people probably have. I compared the two data sets. NOAA has a new data set out called Blue Topo. It's supposed to replace QDEM and some of the other ones. I compared the two data sets, Blue Topo and QDEM, and for this area, I did not see a difference. But I'm sure some of it's better than QDEM in some places. QDEM can be pretty smoothed. And then for the non-tidally influenced water bodies, I used vector data from from NHD. And confirmed that NOAA's deep water bathymetric data here can be wonderful, but is problematic here. The problem was how poorly it matched the depths of the more recent hydrological surveys. At first, I thought it was a simple unit conversion issues, fathoms to meters to feet, whatever it was, but it was not. There was just so many elevation disparities that I found it unusable, which is part of the reason why the map is cut off at the side. By using high-resolution data to describe the salt marsh, I was able to call out many details and textures that are integral in the marsh and unavailable or diminished with traditional cartographic wetland styling. The ditching, for example, the fine orthogonal lines seen throughout the marsh was dug in 2 stages. The first was the 1600s when colonists tried to dry the area for their livestock, and the second was in the early 1900s when they attempted to control mosquitoes. The hypsometric tint also begins to describe the arrangement of the high and low marsh systems and the marsh's gradual ingress into the uplands via the river corridors. What this does not do well is lay low in the visual hierarchy. You'd have to adjust the colors and probably come up with a different scheme. This technique is best when the marsh is the focus of the map and there is time to budget to complete the work. It does take time. Alternative approaches. I'm not sure those colors came out well, but anyway. Even though Katahdin is far from being a coastal wetland, it has a large and unique black spruce dominated wetland known as the Klondike. To capture the moisture gradient, I used a topographic wetness index model, a TWI, to create a tinted shaded relief map. And this is the map on the left. TWI calculates topographically based wetness potential on a gradient from drier to wetter. Since it ignores precipitation, soils, and aspect, it is limited, but it can be useful for preliminary hydrological work. As I did with the Great Marsh, I separated layers for greater color and texture control into dry and wet layers, the orange and the blue in this area. And I had several layers of the blue, actually. Along with numerous hillshades, I also added a flow accumulation raster to help define the surface water inputs. This map captures the moisture gradient well, but needs to be ground truth for the presence of wetlands. And spoiler alert, TWIs don't work well in tidal environments. They do not compensate for tidal inputs. If the budget is super tight and there's no time to gather, process, and render elevation data, consider using a variation of the classic wetland symbol, which we actually saw in Jovian's slides, an early USGS symbol of just horizontal lines. One without the herbaceous growth element. The map on the right uses National Wetland Inventory to show a forested shrub-scrub wetland. Using simple broken horizontal lines recalls the classic symbol, which will then encourage recognition as a wetland, but doesn't make the mistake of identifying the incorrect vegetation. So we're not saying it is a salt marsh or a marsh with cattails. Layering this over a faint blue or gray-green polygon with faded edges suggests the moisture gradient of a wetland and helps hide poorly aligned NWI data. If anybody's used the NWI data, I think most of us know how poor the alignment is. So this helps fudge that factor. This also has the advantage of keeping the wetland low in the visual hierarchy without losing its presence. So in this map, the map for Acadia National Park, obviously the wetland is not, there's no trails there. There's no reason to talk about it except that it's an important part of the environment. So we keep it low in the visual hierarchy. I tend to use this technique in most of my recreation maps these days. I think the potential for expanding traditional wetland styling is vast because wetlands, and particularly coastal wetlands, are at the forefront of conservation and climate change mitigation. They deserve some cartographic attention. And while I'm most interested in how effective elevation data is in capturing the moisture gradients that are part of every wetland, there are options available in the vector. Whoops. In the vector world, consider reviewing NatCase's presentation on Wednesday, 10 tips for historically evocative maps. He notes several ways to incorporate horizontal lines, which could be very effective for showing wetland gradients. I encourage everyone to explore new ways to show wetlands. They are incredibly important. But in short, thank you for your time. I think I'm a little short on time. I actually scheduled this for about 10 minutes, but I think it's late in the day, so I think that's fine. Disconnect. Sorry, guys.
Thanks, Margot. You did great on time, but overall, we're gonna try to keep. We're a couple minutes. Yeah, we're fine. But we're gonna introduce Daniel Coe. Daniel makes earth science graphics for the Washington Geological Survey and maps river systems for meander and flow design. He lives in Olympia, Washington, and enjoys staring at tall trees, foraging for mushrooms, and making art with his kids.